Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about entropy flow and entropy production. First, entropy is a property associated with the second law of thermodynamics. The tasks to be solved by the second law are all related to the parameter of entropy. The entropy and its change are applied to judge the direction, the conditions, and the limits of a process. Therefore, the entropy parameter is the core and the focus of the second law. Entropy is a somewhat abstract property, and it is difficult to give a physical description of it without considering the microscopic state of the system. Entropy is best understood and appreciated by studying its use in commonly encountered engineering process, and this is what we intend to do right now. For the internally reversible process, the formal definition of entropy is: for the internally reversible process, the first law is: entropy is an extensive property of a system and sometimes is referred to as total entropy. Entropy per unit mass, designated S, is an intensive property and has a unit. The term entropy is generally used to refer to both total entropy and entropy per unit mass, since the context usually clarifies itself which one is meant. The change of entropy for the internally reversible process then is: we then have entropy flow, and we have entropy production. The entropy flow is owing to the heat exchange between the thermal system and its surroundings, and can be positive or negative. The entropy production is owing to the heat production of work loss inside the thermodynamic system and is always positive. 2. Now, let's talk about the entropy flow and entropy production in an internal imbalance closed system. The change in entropy during a time period should include the entropy production due to heat transfer within the thermal system, in addition to the entropy production due to entropy flow and heat production. Suppose there is a thermodynamic system with a non-uniform temperature, which consists of two parts, A and B, with uniform temperatures. Due to the unequal temperature of the two parts within the time period, part A transfers heat to part B. For the entire thermal system, including the two parts of A and B, the algebraic sum of internal heat transfer must be equal to 0. The algebraic sum of the internal entropy flow caused by internal heat transfer, however, is always larger than 0. This is also the entropy production caused by internal heat transfer in this unbalanced thermodynamic system. By extension, if an internally unbalanced thermal system is composed of n parts with uniform temperatures, then we have the sum of internal heat transfer, and we have the entropy production for this system. If an internally unbalanced closed system is divided into countless parts of which each temperature is balanced, and then the entire volume V is integrated, then the entropy production caused by heat transfer inside the thermal system and the entropy production caused by heat production are. Integrating along the external surface area A of the entire thermal system, the entropy flow then is. The entropy change of the closed system in d tau then is. Okay, that's all for this task. Thank you very much, and see you next time.